Hello everyone and welcome to this presentation. My name is Adamos Christou and I'm a researcher at the University of Glasgow. I am a member of the Bendable Electronics and Sensing Technologies group, and today I will present to you our work on the influence of the vertical alignment of nanowires on the quality of printed electronic layers. I will begin this presentation by talking about the use of inorganic semiconducting one-dimensional materials for high-performance large-area electronics. I will then present a study on quality of zinc oxide nanowire electronic layers obtained with contact printing, where I will be comparing zinc oxide nanowires grown on different substrates. Then I will move on to conclusions. When considering high-performance large-area electronics, some next-generation applications come to mind, which include electronic skin for interactive robotics, large-area displays, foldable devices, Internet of Things, and smart cities. Importantly, for many of these applications, there is a need for devices to conformably cover non-planar surfaces, and therefore interest arises for flexible devices. However, current high-performance electronic devices and systems are rigid, as they rely on planar silicon-based technology. At the same time, the alternative organic semiconductor-based flexible electronics are also insufficient because the current performance is not on par with high-end electronics. Inorganic semiconducting one-dimensional materials such as nanowires and nanoribbons have great potential to be used as building blocks for large-area electronics, where high performance is required. Nanowires offer solution processability, excellent electrical charge transport, and flexibility, and can be used as active channel or electrode material. Among the various inorganic semiconductors, nanomaterials of zinc oxide have been widely explored and have been used for developing low-power transparent electronics and sensors. Zinc oxide has several unique electrical and optical properties, such as wide bandgap, high excitation binding energy, and excellent thermal stability, as well as high channel mobility. One of the biggest challenges we are currently facing is the integration and assembly of these nanostructures to create electronic layers with well-defined locations, high reproducibility, and uniformity. There are several methods, dry and solution-based, which have been used to assemble nanowires. Solution-based techniques use nanowire-based inks, but these often suffer from things like surface contaminations and reorganization of the nanowires when they are transferred from the air-liquid interface onto the target substrate. On the other hand, dry techniques such as contact printing can help solve some of these issues. Contact printing is a dry single-step process which allows us to print highly aligned nanowire layers on both rigid and flexible substrates. It can also be easily scaled up for large-area electronics manufacturing. To do this process, we begin with a donor substrate with grown vertically oriented nanowires. We then press the donor against the receiver substrate and slide it while maintaining the applied pressure. As a result, the nanowires break from the donor substrate and transfer onto the receiver, and because of the shear forces between the substrates, the nanowires align along the direction of sliding. The contact printing process requires epitaxially grown vertically aligned nanowires on planar substrates. The epitaxial relationship of zinc oxide nanowires with the growth substrates affects the alignment of the wires during the growth process. In the study that I will present next, we compare zinc oxide nanowires grown on different substrates, which are 100 silicon and C-plane sapphire. In this study, we are examining the quality of the contact printed nanowire layers obtained from these zinc oxide nanowire donors. To synthesize the zinc oxide nanowires, we used the vapor phase transport method in a horizontal tube furnace. The growth happens by carbothermal reduction of zinc oxide nanopowder on silicon and C-plane sapphire substrates. Initially, we deposited 2 nanometer gold film on the substrates using an electron beam evaporator. Then we place the substrates and the source material, which is zinc oxide and carbon powder, in a tube furnace in argon ambient. Here we show SEM images of the grown nanowires. On C-plane sapphire substrates, we observe high density of highly vertically aligned zinc oxide nanowires. On the other hand, we get low density of tilted and vertically aligned zinc oxide nanowires on the silicon substrate. We then use the grown nanowires to fabricate electronic layers with contact printing. To carry out the process, we use a custom-built system which allows us to precisely control the various printing parameters. Specifically, we are able to control the applied pressure and the sliding velocity during the process. Also, the system uses self-aligned platforms which ensure a conformal contact between the donor and receiver substrates. For this study, we used silicon receiver substrates. Here you can see SEM images of the printed nanowire layers from the 2 different donors. We use image analysis software to process these images in order to extract information about the printing performance. And some of the figures of merit that we use to evaluate the quality of the printed layers are nanowire density, length, and alignment. In terms of nanowire density, the extracted value is more than double for the sapphire samples at 1.3 nanowires per micron compared to 0.57 for the silicon samples. The nanowire length can also affect density. However, for these samples, the length is similar at around 3.6 micrometers. For the alignment, we consider nanowires to be aligned if they are within plus or minus 5 degrees of the direction of sliding. From the SEM analysis, we observed that for both donor substrates, more than 93% of the printed nanowires were aligned. From these studies, we have derived that the quality of the printed electronic layers is affected by the alignment of the nanowires on the donor substrate. The C-plane sapphire donors had high density of vertically aligned nanowires, and this translated to higher density printed layers. The lower density of partially and completely vertically aligned wires on the silicon substrate produced lower density printed layers. The alignment of the printed nanowires, on the other hand, does not seem to be affected by the alignment of the nanowires on the donor. This result demonstrates that the contact printing process is able to align even tilted nanowires thanks to the shear forces present during the sliding motion. To conclude this presentation, I have discussed the contact printing of inorganic semiconducting 1D materials for fabricating high-performance larger electronics. I have presented a study on the quality of zinc oxide nanowire electronic layers obtained with the contact printing method, where we compared zinc oxide nanowires grown on different substrates. Finally, with this study, we demonstrated how the vertical alignment of grown nanowires impacts the contact printing process. At this point, I would like to thank the Engineering and Physical Sciences Research Council for supporting this project, as well as the members of the Bendable Electronics and Sensing Technologies Group for their help and support. Thank you for attending this presentation. Please feel free to visit our group's social channels for more information on this work, as well as our other projects.